In alternating current circuits, we have combinations of circuits like LR circuit, LC circuit and RC circuit. In the same manner, there is one more circuit, that is LCR series circuit. Let us take up each circuit in a detailed manner. LR circuit of AC. We are having in this one inductance and one resistance. Both now are connected in series across a source of alternating EMF. When we consider there is an inductance this way, there is a resistance this way, both are now connected in series across an AC source of EMF is equal to E naught sin omega t. This inductance is L, resistance is R. Let us now consider the potential difference across this one as VL. The potential difference across the resistance, let us take it as VR. And we know in the case of alternating current circuit, when alone resistance is connected, both current and EMF are going to be in the same phase. That means the difference between the phase or the phase difference between current and EMF, that will be 0. That is the case in a resistance circuit. Therefore, I just write down the same thing here. If I take the virtual value of EMF as EV, the virtual value of current as IV, both are going to be in the same phase as far as resistance that is concerned. But we at the same time know across an inductance, current lags behind the EMF by pi by 2 radian. In other terms, EMF leads the current by pi by 2 radian. The same thing we can show that one here. When I consider this one is the virtual value of EMF, current is now lagging behind this one. The virtual value of current lags behind this EMF by pi by 2 radian. So you can understand in the case of an inductance circuit, current is lagging behind EMF by pi by 2. In the case of a resistance circuit, both the current and EMF are in the same phase. This is the identification one should have. Then what I can write as the relation between these two voltages? When I just plot the phasor diagram for this, you will be finding this as the value of VR. Along the same direction of VR, you will even be finding the virtual value of current also. Whereas in the case of inductance, when current is in this particular direction, when I show like that, this EMF is leading the current by pi by 2 radian. Therefore, you will find the direction for VL will be like this. If I take the same is the direction for virtual current, then you can find that this virtual value of EMF or the voltage across the inductance that now leads this current by pi by 2 radian. In fact, in alternating current circuits, these voltages, we used to take them as vectors. When the direction of VR is like this and direction of VL is like this, one can understand the resultant of these two will now be along this direction. That is what we should call it as virtual value of EMF. That in fact is the resultant of these two values. If we consider this EV is making an angle, say phi, with the direction of VR, then how to just calculate this value of EV in terms of these two voltages? That is one area we have to concentrate on. And the second thing is how to calculate this value of phi also in terms of these two voltages or the potential differences across the resistance and across the inductance. So we just want, first of all, what is the formula for EV? When you know that these two are at right angles to each other, according to parallelogram law of vectors, EV can be written as root under VR square plus VL square. Since the angle between them is 90 degrees, the resultant will be VR square plus VL square whole under root. But one can understand directly, according to Ohm's law, VR can be written as I virtual into R whole square I can write. Virtual value of current into resistance is the potential difference across the resistance connected in that circuit. And of course, you can write VL also in the same manner. Virtual value of current into XL whole square we write. What is this XL here called? It is inductive reactance. That is the resistance offered by an inductance for that AC. That is what actually we represent it as XL. When I rewrite the same equation taking out this IV, what is left here you check? R square plus XL square. This now becomes the virtual value of EMF. Therefrom we can write a formula for virtual value of current as virtual value of EMF divided by root over R square plus XL square. This value we write it like this, EV by Z we write, and that Z we call this one as impedance. What do you mean by this word impedance? Impedance is nothing other than the resistance offered by the resistor and inductor together. This is the net resistance offered by the resistor connected in the circuit and the inductor connected in the circuit. Both put together, they offer some resistance in the circuit. That only we are calling it as impedance. The moment we write it as impedance, what is its formula? Z now becomes root over R square plus XL square. This, in other words, we can rewrite it like this as R square plus XL can be written as omega L whole square, we can write like this. And this Z is going to have same units and dimensions of electric resistance itself. So this also is to be termed as resistance only. That is the net resistance offered by the total circuit, consisting of one inductance and resistance connected in series. That itself we are just giving it as impedance. So Z is equal to root over R square plus omega L whole square also we can write. Now coming to the next concept. What is the angle made by this virtual value of EMF with the horizontal? With the horizontal means with the direction of VR. That also we can calculate here. That is, if I take tan phi from that equation. Let us check this figure. I just want tan phi for my equation now. Tan phi is opposite over adjacent. Opposite value is going to be VL. By adjacent side value will be VR. So tan phi we can write it as VL by VR. At the same time, you can even rewrite the same this way. Virtual value of current into XL divided by virtual value of current into resistance. When that virtual value gets cancelled, XL by R, that now becomes tan phi for us. What is this XL again? It is omega L by R. Therefrom you can rewrite it like this: phi is equal to tan inverse omega L by R. This is actually the equation one should remember to know the angle made by this virtual value of EMF with the direction of VR. So as far as LR circuit that is concerned, what are the important features we have to remember? First thing is, what is going to be the value of current, that is virtual value of current in the circuit. Then after that we need to know what is impedance of the circuit. What are the different formulae for that? Then finally we need to know what exactly is the angle made by this virtual EMF or virtual value of EMF with reference to or with respect to the direction of VR. So these areas one should be thorough with as far as LR circuit, which of course is a series circuit of AC, that is concerned. Let us take one more circuit like this, which is CR circuit. One capacitance will be there, one resistance, both are connected in series in the same alternating current circuit. That is CR combination. CR circuit of AC. Let us take here one capacitor connected to a resistor like this. A source of alternating voltage E is equal to E naught sin omega t, that's connected in series across the system. This is having a capacity C. Its resistance value is given as R. The potential difference across this capacitor we shall take up Vc. Across the resistor we shall take up VR. But again we know, as far as the resistance that is concerned, both virtual values of alternating current and alternating voltage are in the same phase as far as resistance that is concerned. Therefore, we can show this virtual value of alternating EMF and virtual value of alternating current, both are in the same phase as far as the resistance that is concerned. Now come to the next one. This is the capacitor what we have. In capacitor circuit of AC, we can understand that the current leads the EMF by pi by 2 radian. In other words, EMF lags behind current by pi by 2 radian. So whatever be the case, we can directly show this is the direction of virtual value of EMF. Now current leads this EMF by pi by 2 radian. So I can show the same thing upward like this. The angle what we are finding between EV and IV is 90 degrees, which is pi by 2 radian as such. So this is actually the difference between these two individual entities. As far as resistance is concerned, both the values of alternating voltage and alternating current, their virtual values I am talking about, they are in the same phase. Whereas here, current is leading by pi by 2 radian when comparing to the EMF value. Now, according to the concept, E now should be equal to the sum of these two values. But we know according to the directions, when we represent the phasor diagram again, this now becomes VR. That itself is the direction of virtual value of current. Now as far as capacitor is concerned, we know the current is leading the value of EMF. So this is current. That value of EMF now should lag behind the current by 90 degrees. Current is leading the EMF by pi by 2 radian is as well equivalent to EMF is lagging behind the current by pi by 2 radian. So we have to show the value of VC vertically downward. That means the current is now leading by pi by 2 radian. As a result of these two, we find the value of virtual EMF, that is virtual value of EMF along this line. Taking that this angle as phi, we once again can write equations related to these three quantities, relating them. So what is the first equation we just want? Virtual value of EMF is root over VR square plus VC square. That is the first equation what we can write. Now VR can be written as virtual value of current into resistance whole square plus virtual value of current into XC whole square, whole under root. And we can all understand well this XC represents capacitive reactance. It is the resistance offered by the capacitor to an AC, to alternating current, that is a point. So we can rewrite the same this way as virtual current, virtual value of current into root over R square plus XC square, that now becomes EV. Then we can rewrite the same this way, the virtual value of current now becomes virtual value of EMF divided by root over R square plus XC square. And this XC square plus R square under root, we represent that one by Z. And Z again is to be called as impedance. What is the impedance in this particular circuit now? It is the resistance offered by both resistor and capacitor. This impedance now can be rewritten this way, it is root over R square plus XC square In other words, root over r square plus xc is 1 by c omega, that much square. So as far as impedance is concerned, in CR circuit, either you can write that one as r square plus xc square whole under root, or root over r square plus 1 by c omega whole square. Now, this Z will have the same units and dimensions of resistance. Once again, you should understand that point. Now, what next we want? What is the angle this EV is making with reference to or with respect to the direction of VR? For that, I can directly write this way: tan phi is equal to opposite side over adjacent side. Opposite side value is VC, adjacent side value is VR. You can even rewrite the same equation this way: XC by R. Then what would be the value of phi here now? This phi is going to be tan inverse XC by R. This is the formula by means of which the angle at which we people are observing directly the value of EV with respect to VR, you can identify. So once again, in the case of CR circuit of AC, the two series circuit we are talking about, the major points to be remembered are: what is the formula for virtual value of current, and what is the formula for impedance, and what is the corresponding phasor diagram for that, and what is the value of phi. So these areas you have to concentrate on as far as CR circuit of AC that is concerned. The next circuit we have here is LC circuit, a combination of an inductance and a capacitance, both connected in series. So when we take LC circuit of AC, one inductance like this, one capacitor this way, both are now connected across alternating EMF is E0 sin omega t. Now we can understand directly from this the potential difference across this inductance coil is VL. Across the capacitor it is VC. Once again, we should understand what exactly is the relation between current and EMF in each of the elements. When we take this inductance coil, current lags behind EMF by pi by 2 radian. So we find this one as EV and this one as IV. The angle at which this is lagging is pi by 2. If we consider capacitor circuit, here current leads the EMF by pi by 2 radian. Therefore, we have to draw this line like this to show that this is virtual value of current and this angle now is pi by 2 radian. So, in the case of inductance, current is lagging behind EMF by pi by 2 radian. In the case of capacitance, current is leading the EMF by pi by 2 radian. Now, as usual, we have to draw the phasor diagram for this. Phasor diagram, whenever we consider, this is the direction of virtual value of current. Then we can say this VL, that is potential difference across the inductance, that leads this current by pi by 2 radian. Similarly, this Vc, what we are talking about, the potential difference across the capacitor, that lags behind this current by pi by 2 radian. So we find that VL upward, with respect to current it is leading by pi by 2, and Vc downward, with respect to current it is lagging behind that current by pi by 2 radian. Now the question is, what would be the effective EMF across the system? So you can now write E virtual is equal to VL minus Vc mod value of it. For example, if VL is greater than Vc, we can write VL minus Vc the outcome. If Vc is more than VL, then we can write Vc minus VL as the outcome. So the mod value refers to simply the difference between these two without taking the sign there into account. So we can write the same this way, VL, it is nothing other than virtual value of current into XL, minus Vc, that is also virtual value of current into XC. One can understand XL as inductive reactance, XC as capacitive reactance. So you can rewrite the same this way, IV into the value of XL minus XC. That is now EV. So what can we write now as far as virtual value of current that is concerned? EV by XL minus XC, whichever is greater, that minus the smaller value. From this one, you can rewrite it like this, EV by Z again. This Z again is to be called as impedance. In this case, this is the resistance offered by L and C together to that AC circuit. So one should understand this one, the Z value can be written as XL minus XC, the difference of these two. That again you can rewrite it like this as omega L minus 1 by omega C, the difference of these two. So Z is going to have once again the same units and dimensions of resistance. So there is no difference between Z and general term called resistance over here. Now this is the way one can estimate the value of impedance of the circuit. What next we want is, what is the resultant of these two? Directly we have taken up the resultant. If VL is greater than Vc, resultant will be VL minus Vc acting along the direction of VL. If suppose Vc is greater than VL, then the resultant would be Vc minus VL, but acting along the direction of Vc. So whether the direction is along VL or along Vc, that mainly depends on which has got greater magnitude out of these two values, such as Vc and VL respectively. So that way we can understand what is the direction of the virtual value of EMF in this particular circuit. So one should remember in this case, what is the formula for impedance, and in which one, in which element we find current is leading, in which element we find current is lagging. So these are the areas one should remember as far as LC circuit of alternating current that is concerned. The circuit next we are taking up is LCR series circuit. In this particular circuit, we find all the three elements. Resistance will be there, inductance factor will be there, and even capacitance also will be there. So we can write LCR series circuit of AC. That is the next one. Let us once again take one inductance coil like this. There is one capacitor connected in series to this, and a resistance also is connected in series to the same system. Here we are connecting alternating EMF, the source of alternating EMF, which is E naught sin omega t, and this is the symbolic representation for the source of alternating EMF. This is L, this is C, this is R. The first thing what we have to take up is the potential difference across the inductance. Let us consider it as VL. Across the capacitor, it is VC. Across the resistor, it is VR. So VL, VC and VR are the potential differences across these three elements L, C and R. Now in the case of resistance, virtual value of alternating EMF and virtual value of alternating current both are in the same phase. There is no phase difference, already we have learned that one earlier. Whereas in the case of inductance, if you take this as virtual value of EMF, current lags behind this EMF by pi by 2 radian. So this is EMF and this one is current. Current is lagging behind EMF by pi by 2 radian. That is the case of inductance coil. If you take the third one, if this is the direction of virtual value of EMF, this will be the direction of virtual value of current, which now leads this EMF by pi by 2 radian. So all the three entities we are observing here. In the case of resistance, EV and IV are in the same phase. In the case of inductance, IV is lagging behind EV by pi by 2 radian. In the case of capacitance circuit or exclusively capacitor, if you take up, this current leads this EMF by pi by 2 radian. So all the three we have taken, and according to these versions, we have to plot a diagram, that is phasor diagram. When I just consider the phasor diagram here, phasor diagram. Let us start this way. This is x-axis and this one is y-axis. On x-axis, we are now considering VR. Obviously, the virtual value of current will be along the same direction. Now, we find the potential difference across the inductance vertically up and potential difference across the capacitance is acting vertically down. We can take these three directions like this. Let us take up this value of VC less than the value of VL, such that we find the resultant of these two acting in the vertically upward direction. But even of course it can be, VC also can be greater than VL. But we are considering an example here that VL is greater than VC. So what we can understand from this one is, if VL is greater than VC. That is the condition for what we are writing the corresponding equations now. If VL is greater than VC, the resultant of these two values, VL minus VC, that will be along the direction of VL upward. And this is the resultant of these two voltages, and this is the potential difference across the resistor. What would be the resultant of these two? That now will be along this line. That is what we call it as virtual value of EMF, which is the resultant of these two values. And we in fact know this total angle is pi by 2. This total angle is also pi by 2. This angle, let us consider this one to be phi. Then what would be the value of virtual EMF of AC? What would be the value of virtual EMF? Virtual value of EMF we just want from this phasor diagram. I can write E virtual is equal to root over VR square plus VL minus VC whole square. Because VL is greater than VC, I have taken it like that, therefore it comes to be this way. Otherwise we can write VC minus VL whole square when we are taking up, the value will not be affected by that. So we can write the same equation this way also. It is root under virtual value of current into resistance whole square plus virtual value of current into XL minus virtual value of current into XC whole square. Directly we can write. This is VL, this is VC, VL minus VC whole square plus VR square. If we take this IV square common and bring that one out of the root, we find this value IV into root R square plus XL minus XC whole square. This now is going to be the virtual value of EMF. Therefrom we can write the virtual value of current is equal to virtual value of EMF whole divided by R square plus XL minus XC whole square. But in reality, this is similar to I is equal to E by R form, where R gives you the resistance of the system. Thereby, we can rewrite the same equation this way, EV by Z again. What is this Z now to be called? It is to be called as impedance again. Impedance of what? In this particular case, it is impedance of LCR circuit. LCR, all are connected in series. So we can write now the same, Z is equal to impedance of LCR circuit. That is the one. And what is this impedance means? Once again we can remember this way, it is the resistance offered by L, C and R to alternating current. Whatever resistance it is offering to the external flow of alternating current across the system, that is what we call it as impedance in the case of LCR circuit. What is its formula now? Z is equal to root over r square plus xl minus xc whole square. In other words, we can rewrite the same this way also, root over r square plus omega L minus 1 by omega c whole square whole under root. So this is the basic formula one should remember as far as impedance of LCR circuit that is concerned. Now the next concept over here is, in this, what is the resultant EV? We have already got the formula like this. What angle this resultant is making with the x-axis I just want. What angle it is making means we used to generally calculate the value of tan phi. What is the value of tan phi from this from this graph now? It is equal to VL minus VC by R. So using this particular equation, one can calculate at what angle the resultant EMF that is going to be observed in this circuit. Now tan phi, when it is VL minus VC divided by R, we can even rewrite the same equation this way. This tan phi is equal to XL minus XC. This is VL minus VC by VR. Now XL minus XC by R we can write like this. So either we can write VL minus VC by VR or XL minus XC by R. But most important concept of this circuit is, what is the condition for resonance? If you just look at this equation, root r square plus XL minus XC whole square we have. By any chance, if XL and XC are numerically equal, then automatically Z becomes R. That means one can understand that particular circuit is resistive circuit. Even though we have L, C and R, all the three in series in the circuit, the effective nature of that circuit is purely like a resistive circuit. So whenever LCR circuit is behaving like a resistive circuit, then one can say that the circuit is in resonance now. So what is the condition for resonance here? XL and XC are supposed to be equal. Whenever inductive reactance and capacitive reactance are numerically the same, then the total circuit, LCR circuit, behaves like a resistive circuit. It is that particular juncture we call the circuit is in resonance. So what is the condition for its resonance we have to take up now. Let us analyze this equation further. Z is equal to root over x square plus omega L minus 1 by omega c whole square. In other words, r square plus xl minus xc whole square whole under root, that is equal to z. I write a condition here. The first condition is this: if xl is greater than xc, then you surely can understand in this particular case the value of xl minus xc will be positive. You can even understand the same thing by considering that equation also. If xl is greater than xc, then I can write that tan phi will now be positive. Check this equation there. XL minus XC by R is equal to tan phi. So when I write XL is greater than XC, then tan phi will be positive. The second condition I just take up over here is, if at all XL is less than XC, or in other words we can say XC is dominant, is greater than XL, then we can write that the value of tan phi now becomes negative. If you consider directly the third case, if XL and XC are equal in magnitude, then we can understand directly tan phi now becomes 0. Then you can all take up this way, when XL is greater than XC, the circuit is said to be inductive. So when can we say that LCR circuit is an inductive circuit? If XL is dominant there, if XL is greater than XC, in other terms, if inductive reactance is greater than capacitive reactance. In the same manner, the second one we can write this way, if at all XL is less than XC, that circuit now will be capacitive circuit. By any chance both are equal, then that particular circuit is resistive circuit. Whenever this condition XL is equal to XC we take up, this itself is the condition for resonance. Condition for resonance in LCR circuit is that the inductive reactance and capacitive reactance both are supposed to be equal numerically. What would be the frequency when the system is in resonance? That is our next question. When we write XL is equal to XC as the condition for resonance, XL of course we write it as L omega. XC we can write it as 1 by C omega. In other words, omega square now becomes 1 by LC. And omega now becomes 1 by root LC. This omega refers to angular frequency. This is the angular frequency in the case of LCR circuit when the circuit is in resonance. So this is one equation we should remember. And the second aspect over here is omega can be written as 2 pi f. 2 pi times linear frequency is called as angular frequency. So when we write 2 pi f is equal to 1 by root LC, then what can we write? Linear frequency is equal to 1 by 2 pi root LC. This is the frequency of resonance there. So this is what we call it as resonance frequency or resonating frequency in the case of LCR circuit. So what exactly one should understand from this one? Whenever the circuit is inductance dominant, then it is understood XL is greater than XC. When it is a capacitive dominance, it has got, then XL is less than XC or XC is greater than XL, we can write. Whenever it is a resistive circuit, then it is understood the influence of the inductance and capacitance, they are being nullified in terms of their voltages. That means what? The value of XL and XC when they are equal. When they are equal, what happens? VL and VC are also equal and opposite. They get cancelled. Then the total circuit becomes resistive circuit. It is at that juncture we can call or we can say that the circuit is in resonance. What is the formula for angular frequency when this circuit is in resonance? That is 1 by root LC. That is the formula we have to remember. Similarly, what is the formula for linear frequency for this? Linear frequency is F is equal to 1 by 2 pi under root LC. That is the concept. So these are the areas one should concentrate on as far as this LCR series circuit of alternating currents that is concerned. And most important of all is this formula for resonating frequency of LCR circuit. In fact, this is the one which can give us an idea that LC circuit, right, or CR circuit, those things of course we can use them as resonance circuits. CR circuit is a wonderful resonating circuit. That also we people have to discuss as far as this equation that is concerned. So if you take F is equal to 1 by 2 pi root LC is the resonating frequency of LCR circuit, which of course is taken in series sequence over here.